All right, so now last time we did vectors, now we're going to do the derivatives and integrals with the vectors. So our vectors, and this is our component form here, these are in terms of t, so it's really not any different from a parametric equation. You have an x of t and a y of t. They are component functions. Ooh, what was that? Oh, okay. Component functions of the parameter t. So again, it's really not, like, we're calling it a vector and it is a vector valued function, but it's really not any different from parametric. Like you have your x variable, like the x motion left to right is in terms of t, and then the y motion vertically up and down is in terms of t. A derivative is still a derivative and an integral is still an integral. Like none of that's any different. So here we're given this vector. Find the first and second derivatives. All right, so first derivative, we're just going to do the derivative of that. So derivative of cosine would be what? Yeah, so negative sine of t. And then derivative of 2t cubed is 6t squared. If you're like, that's it, yep. I think it said second derivative as well. All right, so now we're going to do the derivative of that. So derivative of sine would be cosine. There just happens to be a negative there. So negative cosine of t, and then 12t. So this says find the derivative at 1. So we're going to find the derivative, and then we'll plug in 1. So derivative of just t would be 1, and then the second part of that would be 2t, good, and then you just plug in 1, so it would be 1, 2. So remember a vector is magnitude and direction. So, well, this is like you went 1 in the x direction, 2 in the y direction, like instructions for the direction that you're going. So using these two vectors, we're going to find the derivatives of these expressions. All right, so this would be, and I would do the derivative like secondarily to this. Derivative with respect to t of, and then let's go ahead and do this 3 times v minus u. So let's do the like x coordinate part of it first. 3 times 3t, that would give us 9t, minus 4t would be 5t. So I'm doing the part that's like in the brackets first, so to speak. So now let's do the y dimension for that. 3 times t squared, well, it's just 3t squared, and then minus t squared, what's that gonna give us? 2t squared, good. And then we're just gonna do the derivative of that. That's what this means. This means take the derivative with respect to t, that parameter t. So the derivative would be 5 and then 4t. So for part B, I'm gonna do the derivative like secondarily. So like leave those instructions in there. Derivative with respect to t. We're gonna plug 2t into this vector for t. So if you plug 2t in, you would have 3 times 2t, so 6t. And then if you plug 2t in here, 2t squared, we give you 4t squared, and then take the derivative of that. So that would be 6 and then 8t. Again, for this one, I'm going to do the derivative after I do this multiplying. We're going to multiply 5t times the vector u. So if you multiply this by 5t, what is that going to give you? Good, that'll be 20t squared. And if you multiply this times 5t times t squared would be 5t cubed. I'm sorry, that thing is so noisy. It's just talkative, but it's relatively warm in this room. Relative, I mean, compared to the rest of the building. So I don't like to complain about the noise too much because it's like, at least it's working. What is the temperature? Oh, 69.7. I could deal with it being warmer. All right, and then you do the derivative of that. So that would be 40t and then 15t squared. So again, a derivative is still a derivative, an integral is still an integral. We're going to do the integrals on this side. None of that's changed. They're just vectors, which is really like parametric. You have an x function and a y function in terms of t. I threw this next question on here simply so that we could review what continuity is. You have to have 3 things for continuity. This is back from unit 1, boys and girls. What do you need for continuity? There's 3 things. A point, a limit. They have to equal each other. Nice job. All right, so we are trying to prove continuity for t equals -1. All right, so first let's plug in -1. So basically, if you get a result, there's a point there. All right, so if you plug in -1, you get -1, comma 0. All right, so there's a point. All right, then we're going to do the limit. So limit as t goes to -1 for this vector. And we're just going to do the limits separately. So you would have limit as t goes to -1 for just t for that first part, comma, and then you'd have limit as t goes to -1 for this square root. Which is a lot of writing just to say the same thing over and over again. But you would get, if you do this limit as t goes to -1 of just t, you would get -1, and for this one you would get 0. And lo and behold, they are the same thing. So what do we get to conclude? Therefore what? Continuous at t equals -1. So v of t is continuous at -1. Again, we didn't really do much there. I just threw it on there so we could review what continuity is, because it's been since unit 1. We're in unit 8, so it's been a while. All right, now we're going to do the integrals. Again, it's really just a review of how to do antiderivatives, because it's not any different. We're just going to do the antiderivatives of these. So antiderivative for 2t minus 1, what would that give us? Good, t squared minus t plus a constant. I'm going to call that C1, and we're going to do a little bit of writing so that I can explain to you like what this looks like, but I'm going to call it C1 because we're going to get another constant for this one. Antiderivative for e to the -3t. Be careful with that one, because there's an adjustment that you'd have to make. Good, -1/3 e to the -3t plus another constant, but it would be different. So I called it C2. No, that's if you have like x to a power, like if you have like x to the 7th, that would be like 1/8 x to the 8th. The e is itself. So but that's kind of why we're, no, stop it. That's kind of why we're reviewing. All right, so this would be t squared minus t, and then your -1/3 e to the -3t plus this C1, C2. And what you'll see is people will just write one big C for a constant vector. So like, I realize I'm writing the same thing over and over again, but you're gonna be okay. They'll just write it like that, and this is your constant vector. Again, it's just an antiderivative. I made the other ones not have a plus C. Oh, why will the next ones not have a plus C in them? They're definite, there are boundaries, okay? And again, you're just gonna do the antiderivative for this one and then the antiderivative for this one. So antiderivative for 8t, what will that give us? Good, that'll be 4t squared such that 0 to 1. Ooh. Gravity. All right, and then for -3, it'll just be -3t such that 0 to 1. And we're going to do upper boundary minus lower boundary for each of them. It's not going to be bad because the lower boundary I made 0. I didn't feel like we had to do too many problems to understand this concept. Like it's just an antiderivative, right? So if you plug in 1, you're going to get 4. If you plug in 0, you're going to get 0. So 4 minus 0 gives you 4. And then what is this one going to give you? Yeah, -3 minus nothing. So just -3. I threw a weird root into this one so that we could review that. When it says cube root, that really means t to what power? Good, 1/3. So that antiderivative, you're going to add 1 to the power, so it'll be t to the what? Good, 4/3. And so out front, you would need 3/4. Good, such that 0 to 1. And then e to the -t, that would be negative e to the -t, such that 0 to 1. So again, it's upper boundary minus lower boundary. If you plug in 1 here, 1 to any power is just going to be 1 times 3/4 would be 3/4. And then if you plug in 0, you would get 0. So it would be minus nothing. So 3/4 for that one. And here, if you plug in 1, you would have negative e to the -1. There's nothing necessarily wrong with that, but how could we fix it so that there's not a negative exponent? -1/e, good. Put it in the denominator. Now, when you plug in 0, you don't get 0 though. So we're gonna do that minus the lower boundary. When you plug in 0, anything to the 0 power is 1, but it's negative, so it'd be minus -1, so +1. Be careful with 0. A lot of times it's 0, but like for example, with e, it's not. The other one you have to be careful of is cosine. What is cosine of 0? 1. Okay, so be careful with those two, right? We'll do this one and then we'll do another break, all right? You are given an initial condition. That's what this is. Where you started, what can we relate this to? Oh, do you remember the monkey and gopher problem where one of them started and then they moved towards each other? It's just like that, right? Let's do the x dimension first. Started at 2 plus, and then our accumulation did begin at 0. See how this is v of 0? But it might not always be 0, so just be careful, right? But it did start at 0. And we want to go until whenever, so I'm just going to put t. It's kind of poor notation because t is also the variable that's inside of here, but just go with it. It's going to be okay. Technically, you shouldn't have t inside the integral and on one of the boundaries, but like, or like x, like you can make one of them x. I kind of just, it doesn't bother me. Does it bother you? Are you okay? Like, oh, it does bother you? Oh, it does? Okay, here, make this an x. I got you. I fixed it. If it bothers you, I'll fix it. It doesn't bother me. I'm like, yeah, whatever. As long as I get the right answer, I'm kind of like, cool. All right, so antiderivative. This would be itself, but as an adjustment for the 2x, you would need good. Let me get everybody through that though. An adjustment for the 2 would be a 1/2, right? And then half of 4 would be 2. So it would be 2e to the 2x such that 0 to t. So it is 2 plus, and then we're going to do upper boundary minus lower boundary. So for the upper boundary, if you plug in t, it would just be 2e to the 2t. And if you plug in 0, it's not going to be 0. If you plug in 0, anything to the 0 power is 1 times 2 is 2. And there are an awful lot of 2's there, but what's going to happen? Yeah, these ones cancel good, and you just get 2e to the 2t. That was fun. Let's do it again for y. Where did y start? 0 plus, and your accumulation again started at 0, but just be careful, it's not always 0. Say 0 to t, 3e to the x, dx. So that antiderivative would just be 3e to the x from 0 to t. And so upper boundary minus lower boundary would be 3e to the t minus 3. And there's nothing you can do with that, so that would be it. Now to put it together is the final answer. This is x, this is y, so your final answer, this vector, v of t equals, would be 2e to the 2t, comma, 3e to the t minus 3. So that's your final answer, is putting it all together like that. But you have to do them separately. I guess you could do it together. It would be like a whole long string of information. I do them separately. I think that that's easier. But it's where you started plus your accumulation. It's exactly like the monkey and the gopher. So just think back to that. All right, so we're going to revisit all of this particle motion with vectors. So position, for some reason they use R for that, or they'll use like whatever letter they feel like in the problem, really, but R of t, and that's just your vector. And again, you have an x of t and a y of t, which, so it's really a parametric function. You have, your x dimension in terms of a parameter t, and whenever you're doing a word problem, it will actually represent time. And then your y dimension in terms of this parameter t. So velocity, you're just going to take the derivatives of them. And acceleration, you're just going to do the second derivatives. Speed is where it gets a little bit weird for me. I'm going to do my best to explain it. And I even found a little blurb that I found online to like kind of, I don't know, explain it to the best of my ability. But speed is the magnitude of velocity. So let me write this out and then we'll talk about it for a second. And the magnitude, if you recall, is that gigantic square root. Do you remember what goes underneath? This was last class. It's x prime of t squared plus y prime of t squared. So a vector has magnitude and direction. And it's so funny, every time I say that or think about that, did you ever see Despicable Me with the Minions? Do you remember the first movie, the bad guy's name was Vector? He even says that vector has magnitude and dimension. I'm like, you took BC calculus. He's not wrong. Magnitude is, the length of that. And then direction is whatever direction you're going. So let's think back to like before we got to parametrics and vectors, all that, just when we did like regular calc A, B with our velocity and acceleration and all of that. Speed was the absolute value of velocity. Velocity was directional. Like, do you remember the hot air balloon problem we did? Positive velocity, it went up, negative velocity, it went down. But speed is just movement. So it's without the direction. So velocity is a vector, but speed is just a scalar. It's the magnitude without the direction. I'm going to read the little blurb that I found on here because maybe that'll explain it better than I can. Speed is a scalar quantity and velocity is a vector quantity. So velocity has, let me read it exactly. Velocity being a vector has both a magnitude and direction. The magnitude of the velocity vector is the instantaneous speed of the object. So speed is just the magnitude. If that doesn't sit well with you, I just promise it's true. You can just go with it. It is what that is. All right. And then average speed, in case you get asked that. Do you remember if I gave you a list of numbers and asked you to average them, you would add them all up and then divide by however much you've got? Do you remember average value was this 1 over b minus a, and then your integral from a to b of whatever it is? I'm going to run out of room here. There should be a dt at the end. I couldn't make it fit. I'm sorry. So average speed, it's an average value of speed. So speed goes inside of the integral and it's 1 over b minus a. You're dividing by the length of speed. All right, displacement is your integral from a to b of velocity. And so that's going to be exactly what we just did on the other side of the paper. You're just going to do the integral from a to b of x prime of t dt, comma, and then the integral from a to b y prime of t dt. You'll just do them separately. And then think back to when we did total distance. The only difference was it had what in it? It had an absolute value. So it's the same thing here. It's going to be of the speed. So integral from a to b of the magnitude of velocity, which is going to be integral from a to b of that gigantic square root. I'm going to write it one more time. There, I fit the dt on the end that time. So speed is just the magnitude. There's no direction involved with it. So it's just a scalar quantity. I realize that's a lot. That's why I wrote it all out there. It's all nice and neat. It's organized for you. You can look back at it, but a lot of it's really similar. Like we kind of repeated ourselves a lot there. So it's like, it's all connected. I don't want you to view it as all like separate information. It all like goes together. Let's just try an example. We'll do more practice with it next time. Here's our position vector. R of t equals this. Find the velocity vector, the acceleration vector, and expression for speed. All right, first let's do velocity. Again, I realize that all looked overwhelming, but all we're going to do is a derivative. So just remember, it's not actually that bad. So our derivative would be what? 2t, good, and then comma 1. See, that wasn't so bad. This is one of those things, it kind of frustrates me because mathematicians make stuff look super scary when it's actually not, right? And then acceleration vector, we're going to do the derivative of that, which would be good. I was worried we wouldn't get the 0, but good. Derivative of a constant would be 0. And then the other thing they asked for was speed. So that is our magnitude of velocity. So draw yourself a gigantic square root. And again, I went over this when I taught it to you. I like to put the blanks in there, put blank squared plus blank squared, because then you can kind of just fill it in. And we're just going to take the derivatives of those, which we just did right here with the velocity vector. So 2t goes in this one, 1 goes in that one. Just for the sake of being thorough, if you simplify that down, it would be square root of 4t squared plus 1. And then part B, is the particle speeding up or slowing down when t equals -1? Okay, let's review back to before we got to parametrics, just when we did regular old velocity and acceleration. How did you know whether your particle was speeding up or slowing down? Are the same or opposite signs? Okay, so let's do our velocity at -1. And here's our velocity vector. So if you plug in -1, you're going to get -2, 1. And then we're going to do acceleration at -1. But look at your acceleration vector. There's nothing to even plug into. It would just be 2, 0. I'm going to write out the answer, but then don't shut down and stop listening to me, because I want to draw a picture so you can see a visual and understand what's actually going on. So we're going to write out the answer, but then I want to draw a picture here. That's why I left all this room. Velocity, if you go -2 in the x direction and up 1 in the y direction, I'll write over here. You go -2x, +1 for y. That would be something like that, right? Okay, from this starting point. And then what was acceleration? 2, 0. That means you went 2 in the x direction, 0 in the y direction. Are those going the same way or opposite ways? Opposite. So we're going to say slowing down. Slowing down at t equals -1 because velocity and acceleration vectors have opposite directions. And I want to draw that, basically that picture, but a little bit more detailed on the paper for you. Again, please don't stop listening. Just humor me. This is the last thing we're going to do here, and then you can have the rest of the time to work on your homework. I just want you to visualize so you can understand what's going on. Let's draw this graph, all right? Let's plug in some values for t. I think if we just do -2 to +2, we should be okay. Yeah. Those of you that didn't take the quiz yet, this is quiz review for you. Everybody else that took it, do you remember like doing this on your quiz? Okay. So if we plug these values, let's do x first. X is this t squared minus 4. If you plug in -2, that's going to give you 0. If you plug in -1, what is that going to be? -3. 0 will give you -4, and then -3, and then 0. Our y dimension is just t, so it would just be these values. And when you graph it, don't look at the t values. That was just our parameter. When you graph it, you're graphing x and y. So we're going to start at 0, -2, and then go to -3, -1. And then -4, 0. -3, 1, and 0, 2. Now, on the quiz, I capped it for you. Like I said, only draw it between these certain values. I'm kind of just continuing this one on because I didn't have like a domain here, but it's going this direction. That's the orientation on there. And then at what time were we talking about? It was -1, right? So at time -1, that's right here. That's this -3, 1. So that's this point. Velocity goes -2 in the x direction, 1 in the y direction. So this would be your velocity vector. I'll zoom in. And then acceleration, 2 in the x direction, 0 in the y direction would be like this. And your particle is moving like that. But do you see why it would be slowing down until it gets to here and then, anyway. Yeah,